Hey YouTube, it's that time of week. It is Thursday, 1 p.m. Pacific, and that means it's time for another ZEISS Microscopy Micro Minute. You're with your host this week, Nate Cohen. Let's get live from the ZEISS Microscopy Customer Center here in Dublin, California. Now, today, we're going to be talking about flowers, pollen. It's springtime here. This is actually the view from a couple weeks ago on the front side of our building. Flowers are in bloom, and it got me thinking, as my nose was running, as I was sneezing, what does pollen look like? And what does it take to look at pollen? Maybe you've wondered this question yourself. It was a fun activity for me to dive into, and that's what I'm going to take you through today, where I've gone outside our building, collected some of our wild flowers, tried to find the pollen, got it out, and got it into one of our scanning electron microscopes, which is going to be required to see pollen as it's quite small, and we'll find out just how small through our story today. So let me take you through that journey. So we'll be looking at different kinds of pollen here and from different kinds of flowers. Now, this isn't an exhaustive list of all the different kind of pollens of the world. There are some pretty cool ones out there. I'm limiting myself to just what were the flowers outside of our building. So some of the flowers that I found outside of our building are ZEISS Innovation Center, California here. We have, of course, the state flower of California, the California poppy. We had a couple of different monkey flowers out there. They're pretty cool. We had the orange bush and the southern bush monkey flowers. I found a Wartleaf Cianthus. There's the Pacific Madrron. White sage was out there, bearberry, and I think a really cool one as well, and it looks really different from the others, and we'll see this by the end, is the Judish tree. And that's actually these trees that were in bloom in the back there. I don't want to lead you on for too long before you get to see some of these really cool pollen, so I'll actually show you some of the images of our state flower. Now, if the state flower is the California poppy, that must make this the state pollen. And here's what it looks like when we bring the pollen into the electron microscope. We could see a bunch of them here. And in fact, this one caught my attention because it had what looks like, I believe, to be a spider silk that was kind of hooked up on one of those. And let's zoom into that one a little bit more. We could see that nice thread in there, and we really started to see the structure of this pollen, this really spiky, circular object with some of these kind of grooves inside of them. And clearly there's some kind of symmetry, but this isn't maybe the best angle. So I kind of shopped around, drove around on my microscope, and found this one. And I think this is honestly my favorite image from my imaging session I spent with these pollen. Here we see this really nice five-fold symmetry, a really detailed surface, and a bunch of little spikes around it as well. And we'll come back to this image. We'll kind of compare it once we look at some of the others. But before we get into the others, I want to explain how we get this and kind of what makes our microscope special and how we're able to take these kinds of images. So before I can even explain how the microscope works, one of the most important things when it comes to doing electron microscopy is the sample preparation. How do we go from the flower to pictures of individual pollen? How can we see something so small, in other words? So I went around the front of our building and collected specimens from those 9 that I mentioned. Here I've arranged those picked flowers out. We could see that they come from a whole variety of different sizes here. And then what's pretty standard to get a sample into the electron microscope is using a stub. In fact, I have a stub here that I can show you. So just a small, this is the idea of the size of them. So this is one of our standard aluminum stubs. There's a pin underneath. I could go bigger here. Let's see if you can see it on my hand there. So this is the standard stub that we use to get samples mounted into the SEM. And all we do is place a piece of small conductive tape right here on the surface. And then I've taken the flower and I've just, in fact, I have a poppy right here. That the technique really is just like if you were a bumblebee, you would have the tape on here and you would just dab the flower on it and you would be left with pollen right on your stub. And we could see now them arranged in the box here. And here is all the different flowers. And then I got them onto stubs. And to see them all in the box together, I actually have my box sample here. Now, some of these flowers, as you can see, it wasn't that easy. Now, for the California poppy, pretty easy, right? You can imagine I could just get a piece of tape with the stub and dab right in there and get the pollen. But some of these others were pretty closed off. And I actually had to use one of our dissecting microscopes to get a better view and use some forceps and get a little creative. So it wasn't as easy as I thought for some of these. We can see some of those flowers get pretty tiny and finding where the pollen is. And some of these flowers just don't produce loads of pollen. So I was really trying to get what I could out of them. And here we are using our really nice 𝗦cie𝗰𝗶𝗹𝘀. This is our stereo zoom microscope, perfect for sample preparation in the lab. And we had a USB axiocam hooked up to it and was able to snap some of these great photos. Now, what does it look like under the light microscope? I think that really helps put into perspective what you'll end up seeing from the electron microscope. Now, here's a picture of one of those stubs. This is the pollen of one of those poppies, I believe, here. And we could see, even at fairly large magnifications here, it just kind of just looks like some mush that's on the surface. But once we get to high enough magnification, this is, I think for reference, about 100 times magnification on the right side here, you can see the individual pollen grains. And some advantages here of using optical microscopy, we can still see the color of these grains. And I think a big one is, well, it doesn't require having an electron microscope. Now you could have just the light microscope sitting there on your desk. However, if you remember the pictures you saw right at the beginning, this isn't as impressive, right? We can see that it's a circle. We can see that there's an individual grain. We can measure the size, but you don't get a nice feeling of what does the true surface of these pollen grains look like. And that's the perfect use for electron microscopy. Now, you probably heard me say that term multiple times, electron microscope, and you might not have any idea of what that looks like. So I want to make sure we're all on the same page. And this is the electron microscope that I used. This is the ZEISS Sigma 360. It is a SEM, a scanning electron microscope. So there are some three major components, I'll say, to our electron microscope, maybe four. We include the side here. You'll have the electron column that comes down and generates the electrons and focuses the electron beam. That is our Gemini 1 column. Then we have the chamber that the sample goes into and a variety of detectors around it to help us create the image. And that all sits on top of a plinth, which contains the bottom of the vacuum system and all the electronics. And then, of course, to the side, we have to have a way to control it. So it's all controlled through our computer and our software. And we have a control panel with our different focus knobs and brightness and contrast and our joystick to move the stage around. So there are advantages and disadvantages to using electrons. I'll start with the disadvantages. The whole column and the chamber must be kept at a vacuum. Because we're using electrons, this is essentially a small particle accelerator, and those are quite energetic. So we need to get the air out of the way to allow our electron beam to travel through the column and illuminate our samples. So that means, there's no eyepiece anywhere, and I can't just put, my hand in there, right? We have to mount the samples on these stubs, And those stubs go into the electron microscope, and then we pump it down to vacuum. Now the advantage, and this is where we'll see in the data as well, is you can focus an electron beam very, very precisely, and you can actually do so and get it to a size that is smaller than the wavelengths of visible light, allowing us to see details that are imperceptible to a microscope solely relying on visible light. Additionally, nothing is transparent to electrons. So when we look at the surface of something, we will truly see its surface, unlike when you saw the picture of those pollen grains and they were kind of translucent. Like I said, there's no oculars for you to look in. It's not like a regular microscope where you're looking into the side. We actually have to build the picture, and this is where the scanning comes in. So one more quick lesson I'll give you here. How do we make an image in a scanning electron microscope? You have samples mounted on stubs. Then you can imagine if you look at the sample, let's divide it up into a grid. And above it, you have that electron column with the electron gun. So you have the source of the electrons coming down. And those will focus into a fine point and we'll aim it into one spot. The electron beam hits the sample, and then electrons bounce back off the surface, and we detect those. Based off of the number that come back, say that was 8, we assign it a gray value. Then the beam will move over one position and illuminate the next spot. And then we get some new amount of signal that bounces back. Let's say that was 15, and now we assign that a gray value accordingly. And we do that over and over again, and the beam scans across the surface from top to bottom, and then eventually you form an image. So hopefully now you understand, at least at a high level, how a scanning electron microscope works. So now let's look at some of that data. Here's what the orange brush monkey flowers pollen looks like. It was pretty clumped together. This one had lots of pollen. And it had more of this football shape, but it did have, instead of a 5-fold symmetry, it had a 4-fold symmetry. Although some look like they actually had 5 as well, so it's actually pretty interesting that some could be 4, some could be 5 there. Maybe that was actually from a different flower. But let's look at an individual one. And what I think was really neat on this one is that I think we even see a little bit of the either nectar or some kind of other material that was still coating the surface here. Looks to have a very similar spiky outside appearance. And I think this answers that question I asked from the start of why does my nose run when pollen gets in it? One, it's very small. This is as fine as dust. 2, you can see at its microscopic structure here, it's spiky and irritating looking. To help put the scale into perception here, let me zoom out so we have just a little bit larger of a scale bar. We have, remember, a centimeter, and a centimeter can be divided in 10, and you get a millimeter. And you can still see the width of a millimeter. You can imagine it, right? When you look at the ruler, it's that tiny little dash, the space between the 2 tiny dashes. That's a millimeter. This scale bar says that's 20 micrometers. So imagine that millimeter, divide it into 1,000 tiny little gradations between those 2 millimeter marks. That would be a micron. And so just 20 of those. This is approximately, to help you also put it into scale perspective, the human hair is anywhere from 400 to 100 microns thick. So what we're looking at here, these pollen, this is thinner, almost by a factor of 5, than human hair. Real tiny. Now, here's the southern bush monkey flower. This one is actually slightly different, right? These, you could tell they're related plants if you even looked at their pollen, but these look just a little bit longer, slightly different. Then we come to, I think, a totally different kind of related plant. This actually wasn't just a small perennial, but this is a larger woody bush structure. This is the Wartleaf Cianthus, and it made these little cluster flowers. And if we looked at their pollen, they almost looked like small clams. And zooming in on an individual one, instead of having this kind of rotational symmetry, this one really just had this fold right down the center. Pretty cool looking. We'll go on to the Pacific Madrron, and this one, every time I moved to a different sample, I was just really taken away with the different shapes it presented me with. And here we see this is more of a cubic shape, and looking at an individual one, it had this symmetry to it, and there's just a lot going on. You could see even on the inside of them as well. And these were these tiny bell-like flowers here on the right. And if we looked at the white sage, these pollen were even smaller than the ones I looked at before. And zooming in, it had this almost lace-like quality to it. It's really mesmerizing to really zoom into these and see the fine structure that was on these. Just appreciating the sage, and this plant smells great, by the way. Here's a technique I wanted to show off as well. There's different ways that we can form signal inside of the electron microscope. We can be looking at information that's really just from the surface, or we can get kind of a deeper view of the sample, maybe more of a material view as well, using this backscatter detector, and we can kind of make the way the sample looks. Like here we have the nice shadows, it looks more natural to our eyes, whereas here we have a more top-down view into these pollen grains, and it almost makes it look like this was made out of a ceramic. And if I could, print a model of this, imagine how cool that would be if you could hold it in your hand. The bearberry had a kind of cubic structure again, and perhaps, I'm not a botanist, so I'm not an authority to make a proclamation of that these are related, but I mean, these were both flowers from bushy-like plants, and they both were kind of growing in our same area here, and it was kind of cool to see that those tiny flowers on these bushy-like plants, their pollen ended up looking similar as well, with more of a cubic shape. Now, this one maybe wasn't as folded in on itself, but it still was stunning, and there seemed to be even finer detail on the surface. So with the power of our sigma field emission SEM, it's really no effort at all to just increase magnification, especially if you're comparing this to using it to a conventional SEM. It really is easy to get an image like you see here. And if you could appreciate, we're at 25,000 times magnification now, looking at the surface of that individual pollen grain, and there were just tinier and tinier features as we continued to zoom in here. So that scale bar is now in nanometers. So remember when I talked about the scale of what the size of a micron is? So let me see if I could estimate with my hand. That is now a micron. That's 1,000th of a millimeter, and we're seeing detail down to the nanoscale here in our SEM. And this, I think, really drives home the power of electron microscopy and why it's such an important technology. Finally, of the samples that I collected, here's from the Judish tree. And these did actually, the closest they looked, it was kind of more like the sage. I don't think there's a relationship there, but these were some pretty cool ones to see where it just, you can see inside of them where it makes this lacy kind of net, and then deeper on the inside there, I believe, is where you would find the little actual active biological bits that the plant would use for reproduction. And now putting it all together, from zooming out all the way to in, let me just show you a quick little bit I've shown this before on previous Micro Minutes. This is our software that's called Zen Connect as part of our Zen Core software package. And this allows you to build correlative microscopy. In other words, you can correlate two different modalities. And so here we've taken the images from the light microscope and I've imported a little bit of the SEM data. So here's this sample case, got a nice big overview image, and then you can see there's different optical microscopy images from the different flowers, and you really start to get a scale of what the pollen is and how small those little pieces get. But now let's put that into the scale of the electron microscopy images. So if I zoom into this first stub, this was the California poppy flower and its pollen. We'll zoom in again. Here we could see what just looks like yellow dust. Then at about 100x magnification with the light microscope, here's what those pollen look like. We could definitely see they're circulating. In fact, you can get the idea that maybe there's a striation or two on here. We definitely have some more powerful light microscopes that would be able to get even more detail out of these things. But then that's pretty much where, at this scale, is where I start to image with the electron microscope. And now we can push in a little bit further and we could actually see where was that one pollen grain that I got, I think, my best image from. We could zoom in again. And we kind of see the neighborhood that these pollen came from. And with each step, we see the details increase even more. And then here's the one pollen that I think just created the most stunning image for me. And we'll just zoom in here. And we could appreciate the detail across. This is a 4K image I took of this individual pollen grain. And you can see the different spikes and its fine surface here. And that's where I'll leave you. So thanks for joining for another ZEISS Microscopy Micro Minute. We've been live from the ZMCC here. I hope you join us next week. And hopefully the pollen doesn't make you sneeze too much.